Let's wait for a few minutes.
Hello, Dr. Amit, can you hear me?
Yes, sir. Yes. And
you are not
are you
audible.
hearing me? Hello? Yes, other participants, are you hearing me?
Hello.
Yeah, audible to all the participants.
Yeah, now you are also audible.
Okay.
So just let me know when I should start.
Yes, so we are starting it right now, sir.
Okay.
So let me introduce before we start. So basically, today is the last day and we are just about to start the first session that is based on the latency awareness in optical access networks. So this session will be jointly managed by Professor Vijay Janiani, sir, and by me. So first half the session will be covered by Professor Vijay Janiani and rest half will be covered by me. So now I am handling the session to Professor Vijay Janiani, sir. Yes, sir.
Yeah, good morning. I need to share my slides. Amit, can you enable? Okay, yeah, now it is there. Yeah, just confirm slides are visible.
Sir, visible, sir.
Okay, thank you and good morning to all of you. So today we'll be discussing about latency aware optical access networks. Because you know that in today's application, the speed of access is also very important. So latency should be kept to a minimum. Okay, till now you have seen that what is a GPON and also some standards and basic operation of GPON. And I hope you have also understood the concept behind efficient use of resources both at the OLT and ONU. It is very important because the carbon footprint is increasing very rapidly, and although our consumptions are very small per se, but the total power consumption is increasing very rapidly because the number of devices with this IoT and smart cities, it is increasing very rapidly. So we need to take care of that latency and power issues because in future it is going to create a big issue for us. So we need to be careful right from the beginning. So now we'll be focusing in this lecture on this ONU part, that is optical networking unit, which is on the receiver side, the device which is on the receiver side. Now we are actually focusing on the latency issues in this, and for that we go for direct inter-ONU communication, because I will show on the next slide what happens in a conventional GPON and what we are proposing here, that is direct inter-ONU communication. It will give you reduced transmission latency. That is the first important thing. Second most important is it will provide efficient use of bandwidth. We'll see how it is done. Energy efficiency is also there. It will consume less energy as compared to your conventional communication in GPON. Reliability is again a plus point here, and transmission security also, you can say it is slightly enhanced in direct inter-ONU communication. So we'll discuss various techniques of direct inter-ONU communication that will give us opportunity to reduce latency and all the above mentioned advantages. So why inter-ONU communication is important? So normally what happens in a GPON network, by now you must be very much familiar with that you have a OLT here at the central office, and then with the help of a single fiber you are carrying the data, and then there is a splitter here, and then that splits the data to different ONUs, ONU1, ONU2 and up to ONU-N. So this is the general, you can say, block diagram of a GPON network. This may be a TDM splitter or it may be a WDM splitter also. In that case, it is called AWG. So in any optical access network, OLT, that is the central office or the central unit, sends messages to the ONU in downstream transmission. So this transmission is called the downstream. And any communication happening from ONU to the OLT, it is called the upstream. So downstream and upstream. So, and ONU sends the message to OLT in upstream direction. So now what happens for communication among multiple users? Conventionally, ONU sends the message to OLT and then after reprocessing, remodulating, the OLT directs the signal to the destined ONU. So basically what happens in a conventional setup, if this ONU wants to communicate with let us say ONU N, then there is no other alternative but this ONU basically transmits the signal to OLT. There at OLT, this is the signal is perceived and then reprocessed and remodulated, and then it is actually sent again through this whole fiber, and then there is some mechanism that how this ONU-N can receive that signal. So there is no direct communication which is lacking between all the ONUs. So in this process, the signal has to travel the optical fiber twice. So you can see that when the ONU communicates from this ONU to this NU through this OLT and this fiber, you are using this bandwidth of the fiber twice. I mean, one on the upstream and then again on the downstream. And not only bandwidth, you are spending more time. The signal is spending more time because this distance may be very long. It can be up to 20 kilometers. So even if that time will be in nanoseconds or microseconds, but still, as I mentioned, that when we talk of very high bitrate data systems, then this becomes significant. So the signal consumes upstream and downstream bandwidth. The signal requires complex reprocessing, remodulation at OLT. They consume power also. This is because OLT has to receive it and then it has to transmit. So again, the power is consumed at OLT. So energy efficiency is also can be improved if we can think of something better arrangement. So and also signal travel to central office. So obviously when they are traveling longer distance and then to to more number of you can say devices, there might be more chances of getting leaked out, and therefore it is, you can say, somewhat less secure because it is traveling longer and then again remodulating and everything is taking place, so it may be less secure. Now come to this arrangement which is shown in this figure. Figure 1, first of all. This is the conventional PON architecture that I have just now explained, that what is conventional PON architecture. Here you have an OLT, optical line terminal or central office. So let us say if ONU1 wants to communicate with any other ONU, ONUK, then let us say it is communicating at lambda 1. So then it has to actually go through this splitter, go to this OLT, and then from this OLT again it will be coming, and then it is splitted by the splitter, and then it goes to every ONU. And this ONU, because it is supposed to receive it, it will be tuned to receive it. So that is conventional PON architecture. And now what is RN? This is a remote node. So here, this is a conventional arrangement with only one remote node. You call this as a remote node, you can say, or a splitter. SC is the splitter or coupler. So this is one one RN stage PON. Slightly better arrangement or slightly modified arrangement with direct inter-ONU communication is as proposed by these authors in this paper. Here actually what you do is you put a FBG here. As you can see, there is a fiber brag grating put in this. And this FBG actually has the property that I will show you slightly more details of FBG, because it is very important to understand the function of an FBG, because later on all the configuration that we study will be using FBGs a lot. So this FBG concept is very important for you to understand that FBG actually, let me go to the next slide and tell you there what is an FBG. So you can see here FBG is a periodic modulation of refractive index in the core of an optical fiber. So FBG is something which is similar to a normal optical fiber. Only thing is the core is having some modification in the refractive index, and there are some high and low refractive index layers of this. Now, what it does is, you can see this diagram here on the bottom right. This has a very important and very significant property that if any signal, any wideband signal, as you can see, this is the wideband signal. Wideband means it is showing you all colors. So that is how we represent a wideband signal. It is showing from red to green, or it means many wide range of wavelengths are there in this signal. So if this signal is input to this FBG or fiber Bragg grating, then what will happen that depending on the design of this FPG, design means what is the distance between these separations, what is their refractive index change, high and low refractive index layers are there. So how much is the change in the refractive index? Depending on that, I mean, you can change your design also. Depending on that, it will reflect a particular wavelength, which is, let us call this as lambda B. That is the Bragg wavelength. So if you see this spectrum, this is the input spectrum to the FBG, and if you see the output spectrum and the reflection spectrum, you see that a very sharp band, or you can say ideally a single wavelength is actually reflected back. So this is the reflection spectrum, and whatever is left, only that particular this wavelength is reflected, and all remaining wavelengths, as you can see, they are passing through this FBG without any problem or without any attenuation. So you see that in the output spectrum, it is the same as the input spectrum, only this part has been reflected back and this has appeared here in the reflection spectrum. So this is the typical reflection spectrum of a FBG with wavelength. You can see this is the reflectivity, and this reflectivity is basically at a certain center wavelength. And as I said, you can design this FBG in such a way that you can change this, shift this wavelength also, or you can make it more thinner also, so that it is more near to the ideal. So basically what we can say that FBG, if I put an FBG anywhere in the circuit, broadly we can say that if there are a wide range of input signals with the very wide spectrum incident into this, one of the wavelengths will be reflected back, let us say lambda B, and the others, everything minus lambda B, will be transmitted. So that is the function of an FBG. Now let me go back to the previous slide. So here what happens that this circuit in figure 2 is a slight modification of that upper diagram. It has still one remote node, Rn is only one, but here you see that we have put an FBG here at lambda 1. This lambda B is equal to lambda 1. So whenever this ONU wants to communicate with any other ONU, it is transmitting at lambda 1, and then this lambda 1, usually it goes through this complete up to OLT, but here because of this FBG, this lambda 1 will be reflected back from this as shown by this arrow, and this lambda 1 will be basically, it is coming to again all ONU. So basically by use of this FBG, you have avoided this lambda 1 signal to travel from this up to right up to OLT and then through this complete fiber of 20 kilometers and then coming back. So you have bypassed that and you have just made this to reflect from here, and then it can easily. So this is one step ahead in direct inter-ONU. So you see, this is inter-ONU communication, direct inter-ONU communication capability. But this is a very raw, you can say, scheme, because there are many modifications and many enhancements needed in this arrangement. This is just a basic principle. Later on, we'll see that what modifications can be done in this. So what is the challenge with the one stage PON, that is one RN, whether it is with direct inter-ONU or without that, there is a challenge with one stage PON. It has the capability to communicate with all the available users in the network. However, cannot provide communication between small group of users. So let me now again go back to this slide so that you understand it better. Now here what I mean to say is that okay, even in this arrangement, this let us say this ONU is transmitting at lambda 1. It can, if it wants direct inter-ONU communication, it will transmit at lambda 1, it will be reflected, and it can then communicate with all the ONUs. But here there is a problem that, let us say there are let us say 128 of such ONUs, 128 ONUs. So it will always communicate with all of them, whether it wants to communicate with all of them or not. So basically, you need an arrangement that let us say let us talk of a typical scenario in a university. You have different departments there, electronics and computers and civil and mechanical. So we should have an arrangement that if I say that these are, let us say, these four ONUs are in ECE department, the next four ONUs are in CAC, and then maybe some in different departments. So we need to have an arrangement that if this ONU, if it is belonging to ECE department, if it wants to communicate only with the ECE group, that should be possible, or it should also be possible that it wants to communicate with all other ONUs. So that problem is there. I mean, this facility is not there in this scheme. We'll see how it can be implemented. Second problem with one stage PON is more insertion loss at RN due to single large splitter, because you have seen that if there are, let us say, these many ONUs, ONU 1 to, let us say, 256, all ONUs are there. So you need to have a splitter here which is having 1:256 ratio output. So it's a large splitter and it will always consume more power. It will need more transmitted power so that it can actually divide the power into 256 users. So sensitivity conditions of receivers are very stringent, because you need very sensitive receivers if you are using a small power at the transmitter end. Because I mentioned in my previous lecture, if you cannot put a very large amount of power, because it has other problems, non-linear issues and all that. Since the signal is reaching to all the available users, whether signal is intended for them or not, that's less secure. And obviously, because when one ONU is communicating with all of them without the requirement of communicating with all, it will be less secure. These problems can be addressed with two remote node PON stage PON architecture. We'll see now how this two stage PON is working. So now you see in this we have proposed a two stage PON, two RN stage. So one RN is this, which is RN1, and this is a 1 cross M. M can be anything, can be 4, 8, 12. And then at the second level, you have the second RN, that is RN2. So it is a series of RN2. All these are RN2, second stage. And each one of these RN, it is basically a splitter only. This is also a splitter. So this is 1 cross N. This is also 1 cross N. So the total capacity which you are having in this is M cross N. This is the number of users that can be addressed in it. So here you have ONUs 1 to N. Here also you have ONUs 1 to N. but just giving a number that m to mn and n plus 1. So this is the number of, you can say, n number of ONUs in each of this RM. Now let us see what is the advantage of this here. How the downstream transmission is taking place. Downstream, remember, it is from OLT to the ONU. This is the downstream, and this is the upstream. So in this case, now see, this OLT is actually having 4 transmitters. So let us say lambda 1, 2, 3, and 4. This is the usual fiber, which is having 20 kilometer maximum length. Then you have an FBG here, now which is tuned to a wavelength of lambda 9. Let us say any arbitrary wavelength, which is not out of all these 4s. So naturally, this signal, which is a composite signal here consisting of all these wavelengths, it will pass through this FBG without any attenuation, because this is not tuned to any one of these, it is tuned to a different wavelength. So it will now naturally go through this splitter, and this will split into, let us say, 4. Now here we have taken m is equal to 4, and n also we have taken equal to 4. So there are 16 actually ONUs, 4 cross 4, which are supported by this arrangement. So here you see that here lambda 1, 2, 3, 4, they are all 4 wavelengths are split into 4 paths. Each wavelength, all 4 wavelengths are going into each path. Here we have put in another FPG, which is tuned to a wavelength of lambda 5. So still in the downstream, this FPG is not creating any problem. You can ignore this. And then further this lambda 1, lambda 2, lambda 3, lambda 4, again they are split into this. So this is how each ONU will get all the wavelengths, and then it can be tuned to a particular wavelength, or it can receive all 4 depending on the application. So this is the downstream transmission. So nothing, very specific here. It is the same as what you have in a single stage phone. But let us see what is the advantage in the upstream transmission and also inter-ONU communication within ODN or all ONUs. So here in the downstream, in the upstream transmission, and this ODN, this is optical distribution network. So we call this as a combined as a ODN, you can say, optical distribution network. So you see here that let us say this ONU1 now wants to make an upstream transmission and also inter-ONU communication. So this transmitter of this ONU that is having TX and also RX, this transmitter will be having 3 wavelengths, lambda 5, lambda 9, and lambda 10. Now, first of all, let us see simply what happens when it is transmitting at a wavelength of lambda 10. So when lambda 10 is being transmitted by this ONU1, now it will be combined here by this, because this is a splitter as well as combiner. In this direction, it acts as a splitter. In this direction, it acts as a combiner. So in this, in this direction, this lambda 10, because it is unaffected by this will again be combined here in the second splitter. It will go through this, and then it will come out through this, again unaffected by this, and then this you can see it is the direct communication from ONU to OLT. So lambda 10 is the wavelength that is used by this to communicate directly with the OLT as previously done. Now what happens when it is transmitting at lambda 5 and lambda 9? Let's say it is transmitting at lambda 5. So it is transmitting at lambda 5. Now this signal goes here. Now this FBG is tuned to lambda 5. Similarly, all the FBGs are tuned at lambda 5. So that signal will be reflected back from here, and then it will be split because it is again input to a splitter. So it will be split. So lambda 5 wavelength, it is used for direct ONU communication within the same subgroup. that is ODN1. It will not go to any other, because if it, as I told you, let us say this is the ECE department, and the ECE department, one faculty or one HOD wants to communicate with all the within the users, then it can be done in this way. Now, what happens with the lambda 9? Lambda 9 is actually used to communicate. Let us say if this ECE department wants to communicate with all other departments, civil, electrical, mechanical, whichever are on that other ODNs. So in that case, this lambda 9 can be used, and you see that this lambda 9, any one of this, any ONU can do this, ONU1 can do this, ONU4, 3, 2, anyone can do this. So let us say this ONU1 is doing it. So it will transmit lambda 9. Now that will be actually passing through this because it is tuned at lambda 5. Now lambda 9 actually is, this FBG is tuned at lambda 9. So that FBG will reflect this lambda 9, and this will now be split into these four, and then it will go to every ODN. All the four ODNs, they will be getting a lambda 9. So this respective receiver of this, it will be able to receive this lambda 9. Now remember that this distance is 20 kilometers, whereas this complete distance is much smaller than this. This may be less than 500 meters total distance. Okay, so that's why we are, because looking wise it looks that this is small and this is large, but this is actually very small distance, and this is the major part distance, which is 20 kilometers. So this will be, I mean, resulting in considerable saving of the bandwidth here, bandwidth, saving of energy, saving of time. So it is giving you a bit better latency. So as I said, this is a hypothetical example of a university where you can see that you have different departments. The director office, let us say it is the central office or OLT, which is this. So in that case, each of these departments can communicate with each of these with specific wavelengths are assigned. So if I say that this director office wants to communicate with ECE department, it will be transmitting lambda 1, lambda 2, lambda 3, lambda 4 as shown here, as I showed in this diagram. Yeah, this one. So that will be the downstream transmission, and lambda 1, 2, 3, 4, this OLT can communicate with all the wavelengths, all the users. So for each department, these are the same. You can assign different also, but it will be more complex arrangement. Say ECE department wants to communicate with the ECE department itself within the same department. So they will be using a wavelength of lambda 5. But if not, it has to use lambda 9 with all the other departments. So similarly, you can do, and then if this ECE wants to communicate with director office or OLT, it will use a wavelength lambda 10, but not lambda 5 and lambda 9, because lambda 5 and lambda 9 are supposed to be reflected back from the FBGs connected. So this lambda 10 can go directly from ECE to director office or OLT. So the arrangement is made in such a way. So this actually shows you the insertion loss for different remote nodes for different transmission. Insertion loss means that whenever you put a splitter anywhere in the path, it has some loss always, because if this is the number of nodes and number of outputs, it is actually approximately given by 3.5 log to n, where n is the number of ports of splitter. So basically, if you see here in this arrangement, inter-ONU communication, this red curve and this green curve, they represent overall, which is more like a conventional, and subgroup inter-ONU communication. You see that there is a significant amount of power reduction or insertion loss, which is achieved in this. So this is a 4 cross 4, that is M and N value, which I mentioned earlier, 4 and 4, and then total number of users is 16. Similarly, here this is 1 cross M here M is 16, and then it goes to 1 cross N. So N is 8 here. So M into N, that is 16 into 8, and then that gives you 128 users. So here you can see that there is a power saving or insertion loss saving as compared to overall communication. So subgroup inter ONU communication would be much better here. The same thing which I showed in the previous graph, it is represented in the form of log bit error rate and input power needed, basically. So if you take any bit error rate, let's say 10 raised power minus 12, and this is for subgroup intragroup, and this is overall intergroup. So for, let us say, minus 12, you have to supply a minimum input power of let's say around minus 5 dBm, whereas for the same bit error rate, this is actually much higher power is required, because you need a very huge number of outputs in the single splitter. So that's with 1 RN, you have this much power. So it is around 9 dBm. So it's a significant power saving in the inter ONU, because every time you need not communicate with all the ONUs. Why should we communicate with them when we want to communicate in a single subgroup? Now, of course, that power saving will depend on how much time in the day we spend on subgroup communication and how much time we spend on overall. So that calculation also is done, which will be shown in one of the slides. Now, what is the advantage that we have just seen? Two-stage based flexible PON architecture provides the overall inter-ONU communication and subgroup policy. And subgroup also, nearby located ONUs, inter-ONU communication. Based on the requirement and application, inter-ONU communication can be made just by changing the inter-ONU communication wavelength, because we have just seen that you can have M cross N is equal to 4 in one of the examples. So it requires 14 dB less power as compared to complete ONU communication. Now that significant power saving 14 dB which you achieved in this, it is actually a big saving, and that can be used to handle up to 4 times larger subgroups. You can have more subgroups, more number of users, because you have got that additional power and you can utilize it. Or maybe you can reduce your input power transmitted by 14 dB. So even if ideally we are talking about ideal case, it is 14. Even if it is not 14, maybe 10 dB is saving is there, but also that is a significant saving. So subgroup inter-ONU communication is also suitable for secured communication. So because we are communicating the data only in the subgroup only. Yeah. So this architecture which I presented in with 2 remote nodes, it provides, it is shown only for TDM. TDM means we are using a power splitter here, and then it is passively splitting these signals in the time domain. This is a time domain signal. But it can be applied to not only to TDM, it can be applied to WDM PON also. The same thing, which we'll see later on. They do not provide point-to-point communication on a dedicated wavelength. Now that has to be implemented, because I will see on the next few designs that how this also can be achieved. The above architectures do not provide point-to-point communication on the dedicated wavelength. So we'll see later on that how, if we want to do WDM PON, what modifications are required, and if you want a point-to-point, what modifications are required. So basically the next WDM PON architecture that I'll be discussing is, it is for dedicated and broadcasting also. Now, you know what is broadcasting? That broadcasting is that, as I said, if one ONU wants to communicate with all the ONUs, or alternatively, if you have an OLT here So normally OLT signals are the broadcast signal because OLT wants to communicate with, send data to all the signal, all the ONUs together. So this is actually a broadcast. Broadcast you can compare with the point to point. So these two are just the opposite terms. So let us see how that WDM PON design is actually realized by using all these functionalities. So WDM PON network for simultaneous upstream transmission with ONU interconnection capability. Now this is the scheme which we are going to see now in detail. And as you see here, you have a multiplexer or demultiplexer now. It is now a AWG device instead of a power splitter. It is not a power splitter. Actually, it is a more complex AWG device which can actually separate your wavelengths here into different. Because in power splitter, you have seen that if your input is lambda 1 plus lambda 2 and so on, that power splitter will divide all the complete power into different paths. It will have lambda 1 plus lambda 2 and so on. This will also have lambda 1. Of course, power level will be reduced. It will be reduced by n. But all the paths are having all the wavelengths. Whereas in this AWG device, it is not so. It is like this, that if you have here lambda 1, lambda 2 and lambda so on, lambda 1 will be going here, lambda 2 can be routed here, lambda 3 and lambda n and so on. So let us now see how this configuration is working. Yeah. And before I go to that, you see that here there is a multiplexer, demultiplexer. There is a OLT here. N number of transmitters are there, each having a wavelength lambda 1, lambda 2. And each block, actually it is nothing but a transmitter and a receiver combo. And this is one remote node. And now we are using a 50 gigahertz interleaver here also. We'll see what is the function of this interleaver. And on this side, each ONU is like this. Only one is shown here in this expanded form, but each ONU is something like this. So each ONU is having one downstream receiver, which it receives, used to receive the signals which are coming downstream. Then it has a upstream inter ONU transmitter and inter ONU receiver also. So let us see. And of course, these are AWG devices, and we are also using a power splitter here. So in a way, you can say it is a combination of WDM and TDM, because TDM is only used here partly, but mainly it is based on WDM. So now let us see how it is working. It is point to point downstream transmission. Now let us see what is happening here. You see, this is the multiplexer, input multiplexer, and it has, let us say, this 8 number of transmitters, 193.1, 193.2 terahertz. All these are terahertz. You can convert them to wavelength also. So 8 transmitters are there, 0.1, 0.2 up to 0.8. It is at as per ITU grid separation. Now here, this transmitter, actually there is a circulator placed here, and you know what is the function of a circulator. If it has 3 ports like this, any signal here, it goes here, any signal input from here, it goes here, and anything input from here, it goes to this direction. So that is the circulator. It doesn't allow any other path. So here now you see that this through this circulator, this signals are going through this 20 kilometer fiber, all the signals. And because now you have a 1 cross 8 AWG here, not a power splitter. So 193.1 terahertz, 193.2 on the second, and similarly 193.8 terahertz on the bottommost output of this. And then in this direction, this interleaver is actually not doing anything. We'll see what is the function of this later on, but this signal is passing through this. So each ONU is getting its own signal. For example, let us see this 193.8 terahertz, which is coming from here. It is being received by this receiver of ONU 8, that is the downstream receiver. So that is the downstream transmission. It is nothing very fancy because it is just like a usual. But let us see what happens in the upstream end, because we are also targeting direct ONU intercommunication. Okay, now what happens here in this case, you see that here there is a demultiplexer also, and it is having some wavelengths 194.7, 0.8, and so on. Now, what happens when, let us say, this ONU is transmitting at a wavelength of 194.7 terahertz? That is to communicate with the OLT, not for inter ONU. For inter ONU, you will be using a different wavelength. So for let us say this is 194.7, ONU2 is 194.8, and so on. So what will happen here is that it will transmit this as usual. This AWG will combine these signals from individuals, which is 194.7 and so on. Now this is transmitting. ONU1 is transmitting at this wavelength. ONU2 is transmitting at 194.8 and so on. So these signals, again, the interleaver has no role in this because it's a 50 gigahertz interleaver. We'll see its role very shortly. So these signals, the upstream signals, they are combined by this AWG and then they emerge here. And then because again there is a circulator, instead of going here, they just are routed through this, and then demultiplexer is again demultiplexing this signals into individual OLT receivers. So that's upstream. Now, what happens in the direct ONU intercommunication? Now, you see, let us again look at this ONU 8. If it is doing inter ONU communication, now you shift the wavelength of this transmitter of this ONU by 50 gigahertz. So that now your interlevers are now operational. So 195.45. So that is a shift of 50 gigahertz from 195.4 terahertz. So that is a shifting of 50 gigahertz. Now that when this signal actually is going through this, now because of this interleaver is there, so it is actually directed in this direction. Similarly with all the ONUs, any communication which is interleaved by 50 gigahertz, any wavelength, which this will be routed through this, and then it will be going. Now see, all these wavelengths are now, whichever wavelength you are talking about, let us say this is communicating. So this is now a passive 8 by 8 splitter. So this signal will be split into 8, and then these are connected to the individual receivers of ONU, that is inter ONU receiver for all this. So now basically this is what it is doing. It is doing upstream inter ONU communication, that it is communicating with all the ONUs which are present without going through this all the path of up to 20-kilometer fiber and ONU. So I hope it is clear. The above architecture provides point-to-point downstream because it is using AWG, so it can provide point-to-point upstream communication and also inter-ONU broadcasting. Doesn't provide downstream broadcasting because you see there was a problem here, not a problem, but we are gradually moving on to more and more complex designs. Here you have seen that it is transmitting the downstream 8 wavelengths and each one is going to this. But what if wants to broadcast? Broadcast means it wants to send some message to all ONUs together. So we will implement that also in the next design, that how it provides the downstream broadcasting also. Now, to incorporate this feature, that is downstream broadcasting, next architecture is proposed in which two CWDM are connected, one at OLT side and one at RN. That we'll see what these are. So WDM overlay wavelength, which is used for broadcasting in the downward direction, downstream direction, is multiplex at OLT and demultiplex at RN via these CWDMs and diverted. So let us see what this means. So it is exactly the same configuration, but the only difference here is now you have a additional WDM overlay transmitter, which is used for the broadcast. And also two different components, CWDM here and another CWDM. This is just nothing but a similar version, similar type of device, but it is a coarse WDM because it has to, I mean, its function is not as involved as this, because this involves n number of inputs. Here only it will have two inputs. So now this is the proposed scheme. Now let us see how actually it is working. You can find more details in these papers also published. So downstream and with broadcasting transmission is proposed in the proposed architecture. So downstream, how downstream is taking place with broadcasting, because earlier also downstream was there, but there was no broadcasting. So here you will see that in addition to these 8 transmitters, which are point-to-point communication with ONU1, ONU2, and so on, here there is another transmitter. It is called lambda DB. That is, B is for broadcast, D is for downstream. So this complex signal, which is consisting of all the 8 wavelengths or any n number of wavelengths, and this one, they are multiplexed by this coarse wavelength division multiplexer, and then they are combined signal is. So here you can see all the 8 signals plus your lambda BD terahertz. It is going through this. Here is, this is the actually now up to, this is the receiver toward the side. So here on the receiver, you see there is another coarse WDM, which does the function of separating your lambda BD from this, because it's a broadcast wavelength, and then it simply takes it to a coupler or a splitter. Splitter and coupler, you can use the words interchangeably, because in one direction it acts as a splitter, in the reverse direction it acts as a coupler. So actually SC is a star coupler. So this wavelength, which is actually directed here, now that is split into all the output ports, and then you can see this lambda BD is going to each ONU. So this is the ONUs are receiving the WDB wavelength, which is the broadcast wavelength. Broadcast means it is coming to all the this ONUs, all ONUs. Whereas all these 8 wavelengths, they usually, as usual, they go to this AWG, and then each one is going to each one of the ONUs. That is the downstream with broadcasting. What happens in the upstream direction and inter-ONU connection? The same, basically the same mechanism applies here. You can see that if you shift this wavelength by 50 gigahertz, that interleaver comes into operation. It is actually diverting it here, and then it is split with this. And yeah, so same thing. And then yeah, this can also transmit on WD this intermeter wavelength, but it is not required. I think there is some noise. Yeah, I have muted the. Yeah. So this is the same arrangement basically, but here you see that I mean this overlay wavelength is there.
Sir, your slide is not visible, sir.
Not visible. Let me share
Yes,
it
sir.
again. Now visible?
Yes, sir.
Okay. So this is the similar arrangement. I think again there is some noise. Anyway, so
I'm checking, sir.
yeah, okay. So that is the arrangement for upstream and downstream and inter-ONU communication.
Sir, hello, sir.
Yes.
Good morning, sir. Hello. Can I have a couple of questions over here?
Yeah, maybe we can take the questions together at the end. Let me.
Regarding this figure,
Okay. So we'll come back to this figure. Not a problem. Just let me, because otherwise I will break my continuity square. So if you don't mind, we can discuss it later. So this is simultaneous dedicated and WDM overlay upstream transmission. That if you want to do a upstream transmission, WDM overlay transmitter is also there. And this one, actually, this wavelength is it is directly going through this splitter, and then this is going through this and to this. Although this may not be required, but still there is a path available. So this is again a hypothetical example of a university, and you can see the wavelengths for metrics for download upstream and inter-ONU that I have already mentioned. For inter-ONU, there is a interleaved wavelength by 50 gigahertz. Otherwise, you can transmit. Now, we did some calculations also, and in these calculations, we assumed that ONU 1, 2, 3, 4, this bottom table, they are actually, we assumed some distances, 100 meter, 200 meter, 100 meter, 300 meter, 5 different distances. Because obviously, as I said, they are less than 500 meter or even less than 1 kilometer, not more than that. And the distribution of 24 hours among different ONUs. So let's say this ONU 1 wants to communicate, or it is engaged with the CO for 1 hour in a day, 2 hours, here 5 hours. So this is 24 hours. So this is how we divide this. ONU 8 is engaged in 2 hours, 4 hours with ONU 1, 1 hour with ONU 2, again 24 hours. So based on these calculations, we did some basic calculations. This is ONU is communicating with other ONUs via OLT. That is the conventional way. In this ONU, if it wants to communicate with the ONU 2, OLT through OLT 1, it has to go like this. So that calculations we did, I mean, based on with this time constraints, and we calculated that how much time and all that is needed. And that is ONU 1 is communicating with other ONUs directly, proposed way. So ONU 1 here, let us say it is communicating with other ONUs, so it is doing it directly without that need of a OLT, and also communicate with the OLT. That also we have considered in the timing table, that for how many hours this is engaged with this OLT, 5 hours or whatever. So each ONU is actually able to communicate directly. So this is how we do the calculations. We one side latency to travel 20 kilometer fiber is, you know, the speed of light 3 into 10 power 8 meter per second. More accurate is this value. So, and what is the time taken over the fiber? That is the length of the fiber divided by the speed. So 20 kilometers divided by this. So 97.94 microsecond is the time, which is the major latency component in all these GPON calculations. Other components, I mean 20 kilometer fiber is we already did. AWG approximately 5 nanosecond. Interleaver has 1 nanosecond latency and all these. So latency for transmitting data from OLT to ONUX is the sum of latencies due to different components. So obviously the time taken from OLT to any ONUX, it will be the sum of the latency of AWG at the central office, CWDM at the central office. In the previous diagram, if you remember, I told you there is a CWDM and there is a fiber, then there is a CWDM here, AWG here. So based on that, we are doing the calculations and based on these timings, approximate sample timings. So fiber is fiber for 20 kilometers, then CWDM at the remote node. So all this and AWG and CWDM, they have the same latency, so you can combine them. Whereas the latency for direct inter-ONU signal from one ONU to other ONU is given by ONU X, NEX to NEY, that is fiber. Now we are still taking the fiber latency here, but as I mentioned, because here this communication is also taking place on fibers, but so it will have some finite delay or latency, but not as much as this 20 kilometer. So that's why we take latency here for fiber, which is from only in the within the remote node to ONUX, and then interleaver, then SC, that is the coupler or splitter, and then again fiber, which is see from ONUX it goes to remote node, and from remote node it goes to Y. So that's why we take it twice. So based on these calculated latencies between different locations, you can see that these are the locations 1 and 2, and these are the latencies. And then based on the timings, this latency saving, you can see that there is a latency saving. How you calculate the saving? You see the latency of the conventional architecture with which involves OLT, and then the latency of the proposed architecture, which is direct inter-ONU communication. So basically the major part is this one. So this we can avoid, and then you can see the savings, latency savings here in this diagram. So this is energy saving also. I mean, you can convert that saving into the energy, and you because we have assumed some hours of operation. If you put that table in here, I mean the number of hours, then also you can see the saving in the energy. So again, energy saving will be that complete path from one ONU to another ONU through OLT, and this is the direct. And then if you multiply it by the hours, then you can get the saving in the energy. So this is the duration for which OLT and ONY communicate with each other. So that is the saving in the energy. So again, significant amount of energy is saved just because we are not using the resources of OLT, and of course, as I said, practically it may be slightly less. It may be, if not 80, it may be 60, but even then there is a saving in the energy. So now I hand over to Dr. Amit to take this further portion from here, ring-based latency, and I'll be available. We both will be available to answer the questions after we finish.
Yes, sir.
So, Dr.
So, sir,
Amit, yeah.
can I share my slides,
Yeah,
sir?
yeah, I will
Yes.
take. Yeah.
Yeah.
Yeah, is it okay now? Yeah, Amit, is it okay?
Yes, sir.
Yeah.
Okay, so thank you, sir, for giving the various ideas about, say, the latency for the various optical networks. So in some next part. So basically earlier what you have seen, in some architectures we are saving the latency that is only for on, while the next architecture that is for WDM PON. So basically you must have the idea about the TDM PON and WDM PON, and as to support the next generation networks, basically we need to have the TWDM PON, that is the combination of the TDM and WDM PON that comes to be the attractive solution. So basically in this architecture what we have tried to make the TDM PON as well as WDM PON for the downstream directions also. So basically in the previous architectures, if I just go back, so in this architecture basically if you see, then we are transmitting the data for the downstream. So the downstream direction, let me take the pointer. Yes, so for the downstream direction, basically there is communication, or we can say no efficient resource utilization, we can say, but definitely this architecture is useful when we are the lines, or we can say at the dedicated rates. Okay, but definitely this architecture has one advantage, that is to broadcast the data on the WDM overlay wavelength. Okay, but there is no way in this architecture that we can transmit the hybrid TWDM fashion. Okay, and if you just see one more previous architecture that is very common. So in this architecture, we are only providing the downstream transmission that is based on the pure TDM PON. That is by creating more stage, that is two remote node stage. Definitely we are saving some power for the inter-ONU communication, but we can say we are not providing the downstream transmission that is in TWDM fashion. So newly proposed architecture, and that is recently published in optical fiber technology. So basically what we are doing in this, we are multiplexing various wavelengths at the central office, then transmitting these wavelengths, say, to this. And then there is one ring architecture. Basically, if you just see, that is the behavior PON. So there is one ring-based architecture. So basically, in this ring, what we are trying to do is wavelengths that are transmitting downstream direction, and then providing that wavelength to some particular net. Suppose lambda 1, lambda 1, lambda 2, lambda 3, or lambda n that is coming at this point. So the circuit will direct these wavelengths towards this direction. And this direction, basically what happens is they have, so basically these wavelength stream will pass from this FBG and will come at the circulator. Again, the circulator will direct these wavelengths to this place, and now this stream will come at this FBG. Much the function of, so here. So basically the lambda 1 wavelength will reflect from here. It will come to this point again, the circulator 1. And now this circulator will direct this lambda 1 wavelength towards this optical forward to this ring further. And basically then again this lambda 2 will be reflected from the network 2, and similarly network 3 ODN N. So basically what these FBGs are doing in this thing? So this is nothing but it is the multiplexing of the wavelengths. So earlier you have seen you can multiplex or demultiplex the wavelength by using the arrayed waveguide grating, but we can also use this FBG structure to multiplex or demultiplex the wavelengths. Okay, so we'll see how this multiplexing is happening in the upstream direction. So basically for downstream direction, demultiplexing is happening. So now this lambda 1 will be shared by the m number of users that are located. You can say that one particular wavelength is coming and then m number of this particular wavelength. So we can say for this direction, downstream direction, we are providing the hybrid kind of network, that is hybrid WDM TDM PON. So now we'll see how this downstream transmission is happening. So for discussing it, I've considered some particular case just for the simulation purpose, or we can say for explaining purpose. So for this, basically at the office, so those transmitters are transmitting data lambda 1, lambda 2, lambda 3, and lambda 4 respectively. Okay, then we have considered 4 optical four distribution and each distribution 4 ONs. Okay, so it is just a specific case, or we can say the total number of 16 users can be supported in this architecture by using 4 wavelengths. So if we are using the pure WDM PON, then basically we need to transmit the 16 wavelengths from the central office for supporting the 16 users. But this 16 optical network 4 transmitters. Okay, so now this is the downstream transmission. So the transmitter 1, 2, 3, 4 transmitting the wavelengths, let us say 193.1, 2, 3, 4 terahertz. So these wavelengths will transmit to this optical fiber and come at the remote node, or we can say site in this ring. This circulator will basically direct these wavelength or this stream towards this site. Now this is having the back wavelength is lambda 5. Here lambda 5 it means 193.5. Okay, so it will not affect this stream. So this wavelength stream will pass then the circulator, and then from this 3.1, so it will be reflected and come to this optical distribution network 1. So in this only there are 4 ONU 1.1, 1.2 to 1.4. So these 4 ONU this 193.1. Similarly, at this point, then wavelengths 193.234 terahertz will come, and 192 will be reflected from this point. This BG2 is having the back wavelength 3.2. So similarly, this by ODN4. Okay, so now how the upstream transmission is taking place in this architecture. So basically now for the FBG6, FBG7, and FBG8 comes into the picture. So upstream data, then transmit that is 193.5, and again in the TDMA fashion basically. So let us just say at some particular time the ON 1.1 will transmit, at another time 1.2 will transmit, and so on. Okay, so this 193.5 wavelength will come at this point, and now this circulator 1 will direct this wavelength towards this FBG5. Now as 5 has 93.5, so wavelength will be reflected back, and then this this will come towards this FBG1. So now in this FBG1, that is, it will reflect the wavelength, or we can say the 193.5 wavelength will transmit and it will come at this point. And pasting data 3.6. Okay, so this wavelength again will come towards this FBG6, and at this FBG6, this wavelength will be reflected as it is having the black 193.6. Okay, so now at this point, you can see there are two wavelengths. So one wavelength is 193.5 and another wavelength is 193.6. So you can see what is happening here. It is nothing but the multiplexing of signals with the help of FBG. While we were discussing the case for downstream, there was the demultiplexing, and now here it is multiplexing. So now 193.5 and 6 terahertz wavelength will come at this point, and FBG3 is transmitting the wavelength at 193.7 and ODN4 wavelength at 338. So these wavelengths are collected and then combined. So basically, if you just see this point, so at this point, we are getting the 4 wavelengths that are transmitted from the ODN 1, 2, 3, 4 respectively, and then it will again circulate this stream towards this optical fiber. So at the central office, the receiver of the wavelengths. So I will not go in detail. So basically, I've already discussed this AWG structure. Okay, so let me just revise. So let's say if a particular AWG is having wavelength that is 193.9 terahertz, and if there is some particular wavelength stream that is coming at port 1, then there will be the demultiplexing or distribution of the wavelength in such a way that this 193 wavelength will 1.0 at port 2, 194.1 at port 3, and so on. And if the stream is applied at input or port 2 of at input port 2 of this 4x4 AWG, then this distribution will be something like at this point it will receive the 193.9, at port 3 it will receive 194.0, 194.1, and then 194.2. So basically this AWG follows this activity, so the wavelength range will be something like this. Okay, so now let us see how the inter-venue communication is taking place in this case. So communication, this 4x4 will come into the picture. Okay, so now there will be no transmission in this ring. So for this ring, the transmission is only for the downstream or upstream direction. Okay, so now let us see. Is transmitting some data at 193.9, 194.0, 194.1, and 194.2 terahertz. Okay, so these wavelengths are connected to port 1 of this 4x4 AWG, and as this 7.9 will be something like 190.9 will be at port 1, 194.0 will be at port 2, 194.1 at port 3, and so on. So what we can say, suppose this one, then it will at 193.9 terahertz, or we can 193.9, then basically it is able to then it will be able to and so on. Okay, so this is how the inter-ODN communication is taking place. And now this is the case this two is with other ODN. So it's at 193.9, 194.0, 4.1, and 4.2. Now this is applied at this second port, input port. Okay, so now the wavelength distribution will be 193.9 at port 2, 194.0 at port 3, something like this. So when this at one is at 194.0, it will receive ODN 4 and so on. Okay, so this is how basically the inter-ONU communication, inter-ODN communication is taking place. Okay, and this is the internal structure of the optical distribution network. So basically there are for separating the transmitter and receiver. So let us just see how this intra-ODN broadcasting is there, or we can say how this group. Okay, so basically in this case, let us just consider this optical networking net 1 of ODN1 want to communicate with this group. Okay, so then it will transmit at the wavelength 193.5, so then it will come at this point. So basically now there is one FBG, and if this FBG 193.5, okay, it is not on 193.5 for some particular case of intra-ODN broadcasting. So then basically this wavelength will be reflected from this point. So now it will go this way, and this way. And again, now this circulator will pass this from port 3 to 1. Then it will go to this point. And similarly, this wavelength will go here, and this will go here. So now here we have the which is again tuned at 193.5. So this will reflect the signal. So this reflected signal will come again at port 1, and then it will be circulated to the receiver of the ONU2, receiver of the ONU3, receiver of the ONU4. And this is one particular case in which ODN1 is broadcasting the data with other ODN. So earlier in this architecture, what is happening? The broadcasting is within the ODN. Okay, now let us consider to this ODN, to this ODN. So basically, what is of the AWG? So basically, this again, this CWDM basically will separate out two wavelengths. Okay, so if normal wavelengths are transmitted, let us just consider 193.9, 194.0, and 194.1. Okay, and if CWDM ports, okay, so basically at this point 193.9 wavelengths will come here, 194.0, here 194.1, and here 194.2. So now this 193.9 will come at this point, 194.0 will come at this point, 194.1 will come at this point. And now this CWDM basically is separating this particular wavelength, that is 194.2. Okay, so now I have, due to the complex, just start separately. So basically what is happening, so if some signal is coming at port A, port B, port C, port D, these signals are connected to this star. So these wavelengths are coming to port P, Q, R, S. So basically there is one combined. So this P point is connected, P point is connected to here, Q point is connected to here, R point is connected to here, and so on. So basically now what is happening, suppose this ODN the data with other ODNs, then it will transmit data at 194.2. So this 194.2 will come at this point, or we can say at this point. So now this 194.2 wavelengths will be distributed to all the ports. Okay, so from here, so here also. So now whatever data that is transmitted at 4.2 terahertz will be received by the audience located inside the network. So there are lots of interesting features that we achieved in this paper. And this is the performance evaluation basically, so I will not discuss this in detail because we are almost sort of time. Okay, so let me just give you some ideas. So this This is for the inter-ODN, and this is for downstream, and this is for upstream. So you can clearly see here that the performance of the inter-ODN communication is best, as it is not having too much data transmission inside the optical fiber. So basically the other factors or the nonlinear effects will not come into the picture. And for the upstream direction, basically there are multiple users that are transmitting simultaneously. So basically when we are transmitting the multiple data, then the nonlinear effects like the four-way mixing or cross-phase modulation effects will be dominating. So it is having the least performance, but definitely in this architecture, basically, if let's say for some particular log of B are of -9, basically, we are having the receiver power budget within the receiver sensitivity. Okay. And again, this is the same concept which sir has already discussed. So the velocity inside the fiber, that is this one, and there are some components used inside the architecture. So each component is having some latency. So in this case, again, we have tried to calculate the latency. So this concept is also same. And if you want to refer, that you can go to this paper and you'll have more detail. So in this architecture, and this is same, basically we just taken how many hours the registrar office or the various departments are engaging. So the same concept for latency saving. So in this case also we are seeing the latency that is microsecond, that is up to 150 microsecond. Okay, for one particular ODN. And this is the energy saving, that is also very good, that is up to the 70 or 75 watt hour per day. So I think this is the end of this session, and now we are open for your queries. Yes, please. Yes, any questions from the participants, please?
Yes, sir. First of all, we all are really very thankful to Professor Jainani sir as well as Amit sir. You have already given very nice explanation about these basic structures, and we have really got a very good insight about this particular topic and all. So very few little as well as the basic questions that just I would like to ask regarding Amit sir, whatever you were just discussing. Sir, can you just tell me something about what is the significance of a center frequency? Because in your shown PPTs, we have observed that, like, what you can say that FBG, FBG, lambda 5, lambda 6, because sir, as such, yeah, as such, we are transmitting. Yes, sir.
So
it is on
basically,
figure 21.
For distributing the wavelengths, there must be some reference wavelength for each and every component. Okay, so for the AWG, so basically center frequency is nothing but the reference wavelength. We can say whatever the wavelength which will be transmitted at port 1. Okay, or you can say if we are having 193.1 terahertz wavelength at input port 1, and we are transmitting, we are having the center frequency that is 193.1. So basically the phase difference between the input port 1 and output 1, that must be 0. So the 193.1 wavelength will be transmitted at output port 1. So that's why this center frequency is used. And suppose if we are having 193.1 center frequency and we are transmitting the data that is 193.2, so then it must be transmitted to the output port 2. So this is the reference frequency by which this AWG will let know at what port the frequency has to be transmitted.
Okay, okay. Thank you very much, sir.
Hello. Hello.
Yes. Yes.
Thank you, sir. I am Dr. Ashraful Sheikh from Alia University, Kolkata.
Yes.
I have actually listened all these lectures, and it is very helpful, as I also a little bit related with this opti system. And regarding, sir, one figure that is I think 12 figure number, upstream ONU interconnection architecture,
Let me just
where
open the
the
filter.
broadcasting. Yeah.
My slides are visible to you?
Yes, sir.
Yes, sir, it's visible.
You make please.
Particular architecture you're talking about? This one? This one?
Make it full screen, please. Earlier one. Figure number 12.
Figure number 12. Yes, this one.
Yes, sir. This one.
Yes.
So here this interleaver, I think it will consider the FBG port, na? FBG part, na?
The fiber
Interleaver.
plating.
Yes.
Yes, you can say this is one kind
this
of
module. How this interleaver is basically designed?
You can also implement here or insert here the FBG. Okay, that is not a big problem. Yes, so basically it is the filter, one kind of filter, so that is separating out some one particular wavelength. So that is
Wavelength,
the 50 kilohertz tuned. Yeah.
Filtering type of function.
Yes,
Okay.
the
And this
function of
lambda B, which is the broadcasting wavelength, sir, you have actually multiplexed it with CWDM multiplexer.
yes,
But this CWDM multiplexer has two receive wavelength.
yes,
Okay.
yeah,
And that one receive signal is a multiplex signal from the mark itself. So this is a combined signal spreading
yeah.
over
Actually,
a multiple
actually,
wavelengths.
yes. Let me just.
And another signal is your only broadcast single wavelength.
See
You
what is
configure
happening.
the CWDM into two wavelengths. That is my basic question.
No,
Actually,
actually,
suppose I want
let me
to.
just
Yeah.
let me just answer your query. So basically, we are having 8 DWDM signals. Okay, so these signals
Yes.
are very closely spaced. Okay,
Close
so
this space.
now
Yes.
we need to multiplex these signals. So for this, here we are having DWDM multiplexer. Okay, so it is multiplexing these 8 signals. Having CWDM. So you can say the DWDM wavelengths must be very closely spaced, while for the CWDM we can have the spacing of up to 20 nanometer. Okay. So if a particular wavelength range or the signals that are coming in one side of that 20 nanometer, okay, that will be at this point, and another signal that is 20 nanometer far,
Broadcast.
that is coming from here. So basically this CWDM is again using for multiplexing these signals. So at this point we are having the DWDM signals, and at this point we are having broad wavelength. Okay, and
No, sir.
the function of demultiplexer. So the closely
No, sir.
spaced
Here,
and
sir, CWDM. There must be certain frequency settings in the CWDM itself.
yes, there must be.
And
Yes, there must be.
in the
So that's
frequency
why.
setting, I think you need to provide the input frequencies, input wavelengths.
Yes,
Okay.
so basically
So
here we have not mentioned this downstream wavelength. Okay, that's why we have not mentioned. So basically depends on this CWDM. So we can definitely have some particular frequency.
that means I can configure this CWDM with particular two wavelengths. One is your lambda B, and there is your combined wavelength, no?
Yes, yeah.
Which is coming from multiplexer.
Yes.
And one thing more, sir, if I rather making this lambda B separate signal, and if I make that lambda B one of your input signal for broadcasting purposes, so that it can directly downstream
Input
to all
signal from
nodes, all ONU. Yeah, you have used 8 input signal, na? So out of that, if I dedicatedly make one lambda B out of that 8, 7 is your signaling and another is broadcast signal, and then put it in the same multiplexer and send to all the nodes. So it will directly go to all the nodes without using your splitter SC.
So then
Splitter
how
may be
you will
used for upstream in intercommunication, but if I make broadcast signal available to all ONU, then I can make it multiplexed with my main signal rather sending it as a broadcast signal. Is there any advantage out of that?
How you will separate it out at the remote node? Basically, because you need to separate out because without use of power splitter or star combiner coupler, you cannot broadcast. Yes, we have to distribute the signal to multiple streams. So basically, how you will separate it out?
No, suppose I want to send one signal 193.1 to
Hmm.
1. So I have used some demultiplexing AWG that will actually
Yes.
demultiplex that 193.1 towards ONU1.
Yes.
So in the similar way, if I connect and again multiplex in interleaver position, the two signal a 93.1 as and lambda b. Okay, that will be separated at the AWG output, and that two signal again can be multiplexed to send to anyone.
Actually, I'm not
Is it
getting.
possible?
I'm not getting your exact question. Basically, so it will be better if you will call
Okay.
me after
Okay, sir.
after
Thank you.
tomorrow.
I will write you.
Then we'll discuss in
I will
detail.
communicate with you later, sir.
Yeah.
Okay.
Let
Okay.
me comment on this, Dr. Amit and Dr. Mohammed